This video provides an introduction to complex numbers. Now, in the past, equations such as x squared equals -4 or x squared equals anything negative had no solutions, and that's because we were looking at the real number system, and we can't take the square root of a negative number. Now, there are solutions to this equation in the complex number system, which is what we're going to be dealing with when looking at complex numbers. Now, complex numbers are used in electrostatics, hydrodynamics, aerodynamics, and alternate current or electricity. So you may encounter them post-school. Complex numbers are based on the fact that I squared equals -1. So that is our key point. If I squared equals -1, then if we square root both sides, I has to be the square root of -1. So now we can solve these equations, because if I squared equals -1, x has to be plus or minus the square root of -1, or x is equal to plus or minus I. So we can now solve the equations we previously couldn't. So let's look at some examples. Express the following using the complex number system. The square root of -5, in long term, you could say that's equal to the square root of 5 times by the square root of -1. Well, the square root of -1 is I, so that's just square root of 5, I. Okay, part B, 5 square root of -3. You've got your 5, then you've got times by the square root of 3 times by the square root of -1. Square root of -1 is I, so this is 5 square root of 3, I. 4 square root of -9 would be 4 times by the square root of 9 times by the square root of 1. Square root of 9 is 3, so it's 4 times 3 times by square root of I. Sorry, square root of -1 is I. So that's 12, I. Next one, 6 plus 5 root 2. Can't do anything with that 6 because we can't add different types of terms. So we've got 6 plus 5 times the square root of 2 times by the square root of -1. So that's 6 plus 5 square root of 2, I. So we are just replacing the square root of -1 with I in each case. The more you do, you won't need all these steps. Okay, it's really just there to show you what to do in the beginning. Next one says solve 2z squared plus 16 equals 8. I'm going to take the 16 over to the other side and make it -16. So now to get rid of that 2, I divide both sides by 2. So I've got z squared equals -8. So my z is going to be plus or minus the square root of -8. Remember the plus or minus whenever you have a even power. So now I have to play with the square root of -8. Z is going to equal plus or minus the square root of 8 times by the square root of -1. Now the square root of 8 we can simplify to square root of 4 times the square root of 2. Square root of 4 is 2, so that's 2 root 2. So coming back, I've got z equals plus or minus 2 root 2, and my square root of -1 is I. Now looking at powers of I. Now the hint here is to work with powers of I squared where possible. Now why are we doing that? Well, we know that I squared equals -1. Okay, so if we can divide up into powers of I squared, we can simplify these. So the first one's nice and straightforward. I squared is -1. I cubed would be I squared times by I, which is -1 times by I, which is negative I. Okay, I to the power of 6 we could write as I squared all to the power of 3. I squared is -1 to the power of 3, and -1 to the power of 3, it is an odd power, so it's going to end up negative. I to the power of 13. We go I squared all to the power of 6, which would be I to the power of 12, times by I. I squared is -1 to the power of 6 times by I. We have an even power, so this -1 to the power that to an even power would be +1. So we have 1 times by I, which is I. Okay, so the key is, as I said, come back to powers of I squared because you know I squared is -1. A complex number has a real and an imaginary part. So if I say Z equals A plus BI, we usually use Z in complex numbers. So Z equals A plus BI is called the standard form or Cartesian form of a complex number. Now, in this, A and B are real numbers, and I is our imaginary number. So we can express it in set notation that our complex numbers are such that they're equal to A plus BI, where A and B are elements of the real number system. So A is called the real part of Z and may be written as the real part of Z equals A. Okay, so A is the real part. B is the imaginary part and may be written as the imaginary part of Z is B. So B is the imaginary part because it's with the I. A is the real part because there's no I with it. Okay. Now, if B equal to 0, Z equals A, then Z is a real number. Okay, because there's no I in it. So what I'm trying to say here, you've got Z equals A plus BI. If B equals 0, then Z is equal to A, and that's real. Okay, if A equals 0, then Z would equal BI. Okay, so Z equals A plus BI. A equals 0, so we're left with Z equals BI. That's purely imaginary. We have no real part to it. Now, if B can't equal 0, Z equals A plus BI is an imaginary complex number. Now, since all defined numbers are complex, the real number set is actually a subset of the complex number system. So if you think back to our flowchart of our numbers or even our Venn diagram of our numbers, I've now included here the complex number system. So our complex numbers splits into real numbers, which you've been dealing with up until this point. They're numbers that can be placed on a number line, and our imaginary numbers, which deal with I. If you think about it in terms of a Venn diagram, you have your complex numbers now encompassing all our real numbers. Okay, let's look at some examples where we're identifying the real and imaginary part. So find the real part of 3 plus 2i. That's the bit without the I, so that's the 3. The second one, it says the imaginary part of -4 plus 2i. Well, the bit that goes with the 2i, that is 2. Next one, what's the imaginary part of 4 take I? So we're looking at this negative I. So remember, it's going to be -1 because we could have written that as 4 take 1 I. And you always have to remember to take the sign in front. So don't forget that. Now, equality of complex numbers. Two complex numbers are defined to be equal if both their real parts and their imaginary parts are equal. So when you're looking at this here, if I've got a plus bi equals c plus di, that is only the case if and only if a equals c, so our real parts are equal, and b equals d, so our imaginary parts are equal. So let's look at some examples with that. If 4 minus 3i equals 2a plus bi, find the real values of a and b. So my real parts versus my imaginary parts. So that means that 2a has to equal 4 and negative 3 has to equal b. So if 2a equals 4, divide both sides by 2. My a is 2, and that's straight off b is negative 3. So therefore, a equals 2, b equals negative 3. In the next one, find the real values of a and b such that 2a plus 3b plus a minus 2bi equals negative 1 plus 3i. So same thing. Look at your real parts versus your imaginary parts. So 2a plus 3b has to equal negative 1, and a minus 2b has to equal 3. You should see here that we have simultaneous equations. Now, I could times my second equation by 2 and solve it via elimination, or I could rearrange this equation to get a on its own and go 3 plus 2b. So add 2b to both sides. So now I have equation 1 and equation 2. Sub 2 into 1. So I have 2 lots of 3 plus 2b plus 3b equals negative 1. Expand my brackets. 6 plus 4b plus 3b equals negative 1. 6 plus 7b equals negative 1. 7b equals, take 6 from both sides, negative 7. So divide both sides by 7, and I have b equals negative 1. Sub b equals negative 1 into equation 2. So a would be 3 plus 2 lots of negative 1, which is 3 take 2, which is 1. So therefore, a equals 1 and b equals negative 1. And remember to check that you're correct. With simultaneous equations, we can always check that we're correct. And you would do that by substituting back into equation 1. So 2 lots of 1 is 2, plus 3 lots of negative 1 is negative 3. 2 take 3 is negative 1, so I know I'm correct.